Okay, so for the displacement function y of xt is equal to a cosine kx minus omega t, we can also calculate for the slope, or we can derive the slope. The slope of the string, which is our medium, is just equal to the partial derivative of our displacement function with respect to x. So this is equal to, we have a, so we have the derivative of cosine kx minus omega t, so we have negative sine, we have kx minus omega t, and then we have multiplied by the derivative of kx, so we have k. So this is the slope. We can write it as ka, negative ka sine kx minus omega t. And then the curvature of the string can be obtained by taking the second partial derivative of the displacement with respect to time. It's x with respect to x squared. So we copy negative ka, and then the derivative of the sine function. So we have cosine kx minus omega t multiplied by k. So we have this expression minus k squared a. We have cosine kx minus omega t, which is just equal to minus k squared times this whole term here is just our displacement function y of xt. Okay, hence if we're going to divide the acceleration, that is d squared, or partial derivative of y of xt with respect to time, and then divided by our curvature, which is the second partial derivative of our displacement function with respect to x. So we will obtain, we have this one. If you can recall, we have negative omega squared y of xt over negative k squared y of xt. Okay, so this is just equal to omega squared over k squared, which is just equal to v squared, since v is equal to omega over k. Now, if we manipulate this equation so that we have this one, okay, so this is the wave equation. We have derived the wave equation. So we can call this the wave equation. Now let us try to solve these problems. An electromagnetic vibrator sends waves down a string. The vibrator makes 600 complete cycles in 5 seconds. For one complete vibration, the wave moves a distance of 20 centimeters. What are the frequency, wavelength, and velocity of the wave? So we're asked to find the frequency f, the wavelength lambda, as well as the velocity v. So we are given with this 600 complete cycles in 5 seconds. And we are also given with this one. For one complete vibration, the wave moves a distance of 20 centimeters. Now, to solve for the frequency f, we can make use of this information. 600 cycles every 5 seconds. So by definition, the frequency is the number of complete wave pattern per unit time. So we have 600 divided by 5, that is equivalent to 120 cycles per second, or this is equivalent to 120 hertz. We have to make use of this statement. So we have, for one complete vibration, the wave moves a distance of 20 centimeters. So that is exactly the definition of a wavelength, the length of one complete wave cycle. So the wavelength is 20 cm, or in standard units, that is 0.2 meter. And then finally, we can get the wave speed v, which is equal to lambda times the frequency. So we have obtained lambda equals 0.2 meter, and then the frequency, which is 120 hertz, we have 24 meters per second. Okay, so these are now the values of our frequency. So we have 120 hertz for the frequency, and then for the wavelength we have 0.2 meter, and then for the speed we have 24 meters per second. Okay, let's proceed to problem number 2. A transverse wave on a taut string is modeled with the wave function y of xt is equal to 0.2 meter sine 6.28 radians per meter x minus 1.57 radians per second t. Find the amplitude, wavelength, period, and the speed of the wave. So again, we're given with the wave function, and we are asked to find the amplitude. So from the wave function, we can actually see that this is the amplitude. So the amplitude is 0.2 meter. For the wavelength, we need to make use of this equation. So we have k is equal to 2 pi over lambda. So the wavelength is equal to 2 pi over k. Now, the wavelength is equal to 2 pi divided by k. Now, the value of our k is 6.28 radians per meter. So this is in radians. So we have 2 pi divided by 6.28 radians per meter, that is equal to 1 meter. This is the wavelength of the wave, which is described by this wave function. Okay, and then next is to find the period. To find the period, we would need to solve for the frequency first, because period is just the reciprocal of the frequency. Now, in order to solve for the frequency, we have to make use of this equation. Omega is equal to 2 pi times f. Or we have f is equal to omega over 2 pi. Now, the value of our omega is this one, 1.57 radians per second. So we have omega, which is 1.57 radians per second divided by 2 pi. So the frequency is equal to 0.25 per second, or this is equivalent to 0.25 hertz. Okay, now to find the period, we just have to get the reciprocal of our obtained frequency. So we have 1 over 0.25 hertz, and that is equal to 4 seconds. And lastly is to find the speed of the wave. So to find the speed of the wave, we just have to multiply the frequency and the wavelength. Therefore, we have 1 meter multiplied by the frequency, which is 0.25 hertz. Therefore, this is equal to 0.25 meters per second. Okay, so the amplitude is 0.2 meters. The wavelength is 1 meter. And then we have the frequency, which is equal to 0.25 hertz. The period, which is equal to 4 seconds. And then we have the wave speed, which is equal to 0.25 meters per second. Okay, so let's try another example. Now, transverse waves on a string have wave speed equal to 8 meters per second, amplitude equals 0.07 meter, and wavelength 0.320 meter. The waves travel in the negative x direction, and at time t equals 0, the x equals 0 end of the string has its maximum upward displacement. So find the frequency, period, and wave number of these waves. Write a wave function describing the wave, and then find the transverse displacement of a particle at x equals 0.36 meters, at time t equals 0.15 seconds. And lastly, how much time must elapse from the instant in part C until the particle at x equals 0.36 meter next has maximum upward displacement. So in order to solve for this problem, we have to take note of the given first. So these are the given. We are given with the wave speed v, which is equal to 8 meters per second. We are also given with the amplitude, which is 0.07 meter. And then we also have the wavelength, lambda, which is equal to 0.32 meter. And then take note that the wave is traveling in the negative x direction. And at t equals 0, and x equals 0, the string has its maximum upward displacement. So we have this one. Y is equal to a at t equals 0 and at x equals 0. Okay, so first we have to find the frequency, period, and wave number of these waves. To find f, we have to use this equation. V is equal to lambda times the frequency. Therefore, f is equal to v over lambda. So we are given with the value of the wave speed, which is 8 meters per second, and then we have the wavelength, which is equal to 0.320 meter. Therefore, the frequency is equal to 25 hertz. Okay, and then we can easily find the period. The period, so this one is our frequency, F. So to find the period, we have this equation. T is equal to 1 over F. So we have 1 over the obtained value of the frequency, which is 25 hertz. So we have, this is equivalent to 0.04 seconds. And then lastly is to find the wave number. Wave number, which is denoted by K. So K can be obtained by using this equation. We have 2 pi over lambda. So 2 pi, substitute the value of the wavelength, which is 0.32 meter. So we have obtained the value of our K, which is 19.63. We have radians per meter. And then we write a wave function describing the wave. So we are given with these conditions. The wave is traveling in the minus x direction, and at x equals 0, t equals 0, the value of y is equal to a. Therefore, the wave function, the general form of the wave function for this wave is y of xt is equal to a cosine, we have kx plus omega t. Previously, we have obtained the value of k, which is equal to 19.63 radians per meter. And then we also are given with the amplitude, which is equal to 0.07 meter. And we can find omega by using this equation, 2 pi f, where the frequency is equal to 25 hertz. So this is equivalent to 157.08 radians per second. Therefore, the wave function describing the wave is this one. Y of xt is equal to 0.07 meter. We have cosine kx, where the value of k is 19.63 radians per meter, and then we have our x plus our omega, which is 157.08 radians per second t. Okay, so this is now the wave function describing the wave. Okay, so for letter C, we have to find the transverse displacement of a particle at x equals 0.36 meter and at time t equals 0.15 seconds. So our wave function, y of xt is equal to 0.0700 meter cosine kx. We have x plus our omega, which is 157.08 t. Okay, so hence for x equals 0.36 meter and t equals 0.15 second, then we have 0.07 meter cosine we have 19.63 multiplied by the value of our x, which is 0.36 meter plus 157.08 multiplied by the value of d, which is 0.15 seconds. Alright, so evaluating, we have 0.07 and this is 30.6288. Now take note that when evaluating this one, we have to use the radians mode of our calculator. So therefore, we will obtain 0.05 meter. So this is for y of xt, where x equals 0.36 meter and then t equals 0.15 seconds. Okay, so this is the transverse displacement of the string. And then lastly, for letter D, how much time must elapse from the instant in part C until the particle at x equals 0.36 meter next has maximum upward displacement? So take note that the maximum upward displacement is equal to the amplitude A. So we have y of xt is equal to A cosine kx plus omega t. So by this time, we have to find the time with which the particle in part C has maximum upward displacement. So that means the value of our y is 0.07 meter equals, we have the amplitude, which is 0.07 meter, and then we have cosine, the value of our k. K can actually be expressed as 2 pi over the wavelength lambda. X, our value of x is 0.36 meters plus omega, we can write it as 2 pi f times t. So we have 0.07 meter equals 0.07 meter cosine. So we can take out 2 pi. And then we have 0.36 over the value of our wavelength, which is 0.32, plus we have taken out 2 pi. The value of our frequency is 25 hertz multiplied by the time. Okay, so here we can divide both sides by the amplitude. So in the left side of the equation, we have 1 equals, we're left with cosine 2 pi, and then this is equal to 1.125 plus 25t. Okay, so now cosine theta, we know that cosine theta is equal to 1 when theta, the values of theta are 0, 2 pi, 4 pi, 6 pi, and so on. Or this is when theta is equal to 2n pi, where n is equal to 0, 1, 2, 3, 4, and so on. Okay, therefore, we can equate our theta. In this case, we have theta is 2 pi times 1.125 plus 25t equal to 2 pi times n. So we can cancel out 2 pi, or I should say divide both sides by 2 pi. So we are left with this equation. We have 1.125 plus 25t is equal to n. So we have 1.125 plus 25t equals n. Or we have 25t is equal to n minus 1.125, and we divide both sides by 25, so we are left with n minus 1.125 divided by 25. This is equal to n over 25 minus, this is 1.125 over 25. This is 0.04 n minus 0.045. Okay, now at the instant in port C, so at the instant in port C, the value of t is equal to 0.15 seconds. So we can calculate the n at that instant. So we have n is equal to t plus 0.045 divided by 0.04. So this is equal to 0.15 plus 0.045 divided by 0.04. So that is 4.875. Okay, so this is not an integer. The value of n is not an integer as expected, since the y at this instant is not equal to the amplitude a. Okay, so the next integer gives us the value of n corresponding to y equals a. So we have n equals 5. The nearest integer is n equals 5. Therefore, t, we can solve for t at the instant where y is equal to a. That is, we can make use of this equation. T is equal to 5 minus 1.125 divided by 25. This is equal to 0.155 seconds. And thus, so we continue here. Thus, delta t is equal to t final minus t initial. So we have 0.155 seconds minus 0.15 seconds. So we have 0.005 second. So this is the time elapsed. Okay, for our problem number 4, for the transverse wave in the previous problem, what is the velocity function and the acceleration function? And find Vmax and Amax. Okay, recall that y of xt is equal to 0.07 meter cosine 19.63 x plus omega 157.08 t. So to find the velocity, we just have to take the partial derivative of the displacement function with respect to time. So therefore, we have 0.07 meter, and then the derivative of cosine is minus sine. We have 19.63 x plus 157.08 t, and then multiplied by the derivative of the angle, which is 157.08. Okay, so we have this one, negative 0.07 times 157.08 radians per second, that is 11 meters per second, sine 19.63x plus 157.08 t. Okay, so this is the velocity function. And Vmax, to find Vmax, Vmax is just the maximum velocity. So if we have A as the maximum displacement, then we have Vmax as the maximum velocity. So the maximum velocity is plus minus 11 meters per second. So it can be positive and it can be negative. Now, for the acceleration, we just have to take the derivative, the partial derivative of our velocity function with respect to time. So we have negative 11 cosine, we have 19.63x plus 157.08 t multiplied by the derivative of this angle, which is equal to 157.08. 157.08. So we have the acceleration, which is, so we have negative 1728 cosine kx plus omega t. So the maximum acceleration is equal to plus minus 1728 meters per second squared.